The only way to build a truly high maneuvering fighter is to build it in two pieces. One piece would be a high-speed maneuvering platform designed entirely for high-speed flight. The other would be a separate wing designed just for takeoffs and landings, which would have the landing gear on it. This is because a fighter plane has to operate in essentially two flight regimes: low-speed incompressible flow and high-speed, which produces compressible air. The design of wing for those two conditions are completely different, and trying to build a compromise wing means you're compromising the performance and you don't achieve optimal performance. So it requires the separation, which is expensive, difficult, and a real pain, but there's no other way to achieve high performance flight, and planes that don't have it are going to lose in a war. A weak attempt to deal with the difference between low speed and high speed flow was building variable geometry aircraft, swing wing aircraft. This doesn't work. You wind up with wings that are too flexible, and it adds mass, weight to the aircraft, which reduces its maneuverability. Any competent engineer should have figured out this wouldn't work within a couple of hours. It took the geniuses who were doing aircraft design over 20 years before they realized what a complete mistake it was. The F-35 was designed around the belief that a fighter plane can't turn at more than 9 Gs. This isn't true. The turning acceleration of a fighter plane is proportional to the total lift force. To turn at 9 Gs, you must produce 9 times the actual lift of the weight of the aircraft. U.S. fighter planes are designed to have a lift of 90 pounds per square foot wing loading for air-to-air combat. So to achieve 9 Gs, one must achieve 810 pounds per square foot of lift. At sea level, atmospheric pressure produces about 2,100 pounds per square foot of pressure. At 18,000 feet, that is halved to a little over 1,000 pounds. At 15 to 16,000 feet of altitude, it is impossible to achieve much more than 810 pounds of lift per square foot. In order to increase the turning rate, one must then increase the size of the wing. Increasing the wingspan to increase the total area of the wing produces a very heavy wing. If the chord is increased, this does not necessarily have to happen. One of the chief factors used in the design of an aircraft wing is called thickness to chord ratio. It is the maximum thickness of the wing measured from the top to the bottom divided by the chord. If the chord length is increased, the front to back measurement of the wing, the thickness can also be increased proportionally. If the wing thickness is, for instance, made twice as thick, the wing skin can be made half as thin. This is because the principal factor in design of an aircraft wing, structurally, is the stiffness, the ability to resist bending. And stiffness is a function of the distance from the center of the wing skin to the center of the actual wing, times the thickness of the wing, times something called the modulus of elasticity. If the wing chord is made twice as long and the wing thickness is half as thick, the weight remains the same. You've increased the larger surface of the wing without adding weight to the aircraft. The process of increasing the wing thickness and decreasing the wing skin can be done down to the point where the wing skin actually buckles. This is called thin-walled buckling. To further increase the chord of the wing, it would be necessary to, at that point, reduce the actual wing span. All of these steps have reduced what is called the aspect ratio of the wing, the wing span divided by the wing chord. At high-speed flight, that is not that important. At low-speed flight, it loses efficiency, and additional steps would have to be made for takeoff and landing. In fact, a separate wing would have to be built, a lifting wing, to physically pick up the aircraft off the runway and to allow it for it to land. There are two main types of stiffness. One is called bending stiffness, which is the physical movement of the wing tip up or down. The other is called torsional stiffness, which is if you're looking towards the body of the aircraft, actually twisting the wing. This is very important in terms of maneuvering. What happens essentially is that the wing is made up of a section of beam sections, which are the wing spars and the accompanying wing skin. As the wing attempts to twist, each one of these spar combination beams is bent. In addition, there is a chord element that goes from the front to the back of the wing, which also provides structure. There is a two-dimensional structure that makes the stiffness work. Because the wing is thicker through a larger part of its section, when you expand the chord, the wing stiffness greatly increases. The additional stiffness is desirable as it makes the aircraft capable of higher performance maneuvers. If one looks at an aircraft similar to an F-15, the total wing area, the length of the wing through chord, could probably be increased by about 70% before you run out of places to put the wing. This is probably the maximum that could be achieved, although the needs for structural weight may result in some reductions, such as somewhat of a reduction in wingspan for additional chord. An increase in wingspan both increases the amount of force plus times the distance between the body of the aircraft and the center of the force. That produces roughly a squaring effect with increase in wingspan. Similarly, if you decrease wingspan by about 10%, you can increase chord by probably 20% for a net increase of wing area of about 10%. Another option is to have actually a forward swept pair of wings. This could help with balance depending on the overall weight distribution of the aircraft. The other advantage of doing this is that both the forward canard winglets and the main wings are all producing lift. Under a normal aircraft design, the horizontal stabilizer is actually producing a downforce to move the aerodynamic center of the main wings further back for stability. Aircraft wings are actually measured to the center line of the aircraft fuselage. The total shape of the wing is extended until it meets the aircraft center line. In horizontal flight, under non-compressible conditions, relatively low speed flight, only the external part of the wing can produce lift. This is produced by a circulation. As air flows over the wing shape, it actually produces a circulation of wing that moves from front to back on the top of the wing and back to front on the underwing, forming something like a circular or elliptical pattern. This is added to the normal flow of air to produce a higher rate of speed above the wing than below the wing. The circulation increases the speed above and decreases it below the wing. Air pressure is a function of the speed of the wing. The faster the air pressure, the more the pressure drops. Because the velocity is higher above the wing than below, there's a greater pressure drop above the wing and lift is produced. Under supersonic flow, a wedge-shaped object can actually produce lift if it is tilted upwards from the horizontal. The shock waves produce a lower pressure region above the wedge than below the wedge, and this produces lift. Similarly, under compressible flow, relatively high speed flow, if the wedge rotates with respect to airflow, it will produce lift eventually. What happens is the air compresses and then decompresses, and in the process it entrains additional air and eventually forms a circulatory pattern above the surface, which produces a strong amount of lift. There is a classic curve that is produced for Mach 0.8. This curve shows how much lift can be produced under a rotation. It is a factor of up to 5 times what's called the pressure term under US usage, multiplied by the rate at which the wing is rotating in radians per second. This produces an enormous amount of lift and allows for high-speed maneuvering and allows the body of the aircraft to actually produce lift under these conditions. Under incompressible conditions, a wedge cannot produce lift because the circulation can't occur. At the rear of the wedge, the air cannot turn the corner. This is something called Kudda's hypothesis, which is necessary for airfoils to produce lift. The vertical axis is a ratio related to the pressure term. The pressure term is the density times velocity squared. Under American practice, that's divided by 2 to make it look like something called the Bernoulli equation. Europeans don't divide by 2. That's also multiplied by the rate of angular change in radians to produce the total effective force of lift. The horizontal axis is semichords, which is 1/2 the distance from front to back on the wing. With a tapered wing, the various parts, the shorter, smaller chords, would achieve lift before the longer chord sections closer to the body. The semichords come from what is known as conformal mapping. The flow of air around a circular cylinder can be solved mathematically. The coordinates of the circular cylinder are then moved mathematically onto the actual wing shape. This also moves the pressure, and that then enables a calculation of lift. The key measurement in the circular cylinder is the radius. The radius then becomes the semichord. That is why semichords are still used as a measure of distance. The distance in semichords is actually a time measurement. Engineers like doing things like that. But it is actually an artifact of conformal mapping, which is still used. Compressible flow is a continuum. At 180 miles per hour, air only compresses about 3% and can be ignored. The compressibility goes roughly as the v squared. So at higher speeds, it becomes a significant factor. The point at which it becomes significant can be taken as, for instance, at Mach 0.5. This would be about 370 miles per hour at sea level, lower at altitude. There is no reason for a fighter plane to operate below this speed or to be designed to operate below this speed. So designing it entirely for high-speed compressible flow gives you enormous aerodynamic advantages and really does not have any effect negatively upon its aircraft performance in operational modes.